Honor student, this is your last concept in Unit 2, Concept X, where we're going to be focusing on how energy relates to phase changes. So by the end of this video, you should have a basic understanding of energy changes that are involved with the various phase changes, and you're also going to be completing calculations using or involved with heat of fusion, heat of vaporization. So phases of matter, we've talked about particle diagrams, but you should also be aware of how they relate to solids, liquids, and gases. Solids, they keep their shape. They're close together, arranged usually in an organized pattern. Liquids, they take the shape of the container, obviously at the bottom, and they don't fill the container, they keep their volume, but their particles are much more disorganized and able to flow around each other. Gas, they always take the shape of fill the container. Here we would have to have a lid on it in order to keep the particles within it, and they move in constant straight line motion ideally. Now, the phase of a substance depends on three things: the temperature, pressure, and also the nature of the substance. We're going to focus mostly on temperature in this unit, but we're also going to eventually swing this back to pressure and the nature of a substance later in the year. So phase changes, these involve changes in heat energy. However, a phase change does not create any change in temperature. The temperature stays the same amount the entire way through a phase change. Energy is gained or lost is solely potential energy from the interactions that occur between particles. So our endothermic phase changes, these all have to absorb energy. So this includes melting and fusion, which is solid to a liquid, evaporation, boiling, or the more general term vaporization, which is a liquid to a gas. And then also you can have a solid go directly into a gas, which is sublimation. Exothermic phase changes, these are going to release energy when they occur, so such as condensation, which is a gas to a liquid, freezing, which is also called solidification, which is liquid to a solid, and then also deposition, which is when a gas goes directly into a solid. So I like to show students this diagram because I think it helps them kind of see how it's all related together. So whenever you go from a solid to a liquid or to a gas, they have to gain energy in order for the particles to move farther apart from each other, because there's attractions between particles that try to keep them together. So those particles have to gain energy in order to get away from each other. However, when you go from a gas to a liquid to then a solid, those particles, in order to move closer together, have to get rid of that extra energy, and then their attractions pull them back together and eventually into a solid state. So think about how the particles moving, whether or not they have to gain or lose energy in order to accomplish the phase change. Now, heat calculations, yesterday we talked about Q equals mc delta T, but that's only when there's a temperature change. Since there is no temperature change during a phase change, we can't use this formula. So we have two different formulas that we're going to use. The first one is involved with heat of fusion. This is defined as the amount of energy needed to melt a solid into a liquid or solidify a liquid into a solid. Melting would give us a positive Q value because it's going to have to gain energy. If we freeze or solidify a liquid into a solid, that's going to be a negative Q value because it's going to be releasing energy. But both types of phase changes are going to be using this formula. Very similar, Q is heat, M is mass. Our new one is HF, which is heat of fusion. So how much ice can be heated when 1500 joules of energy is available? Well, we can look up our heat of fusion for water. This is probably the trickiest thing for students. They forget that when water or ice is mentioned, they actually have to look up the heat of fusion value, which is 334 grams per joules per gram. So we have our formula. We're going to be solving for mass. Here I've simply just inputted the values in first, and then I'm going to divide each side by 334, which gets me 4.49 grams. So again, I inputted the joules, so the heat of energy amount, and then I've also looked up and inputted the heat of fusion for ice and water. Alright, heat of vaporization is going to be used either when we go from a liquid to a gas, so I vaporize, or a gas to a liquid, which is going to be condensing. And again, the big change here is our heat of vaporization, HV. So here we're going to vaporize 60 gram sample of an unknown. The student has to add 42,512 joules. So what is the heat of vaporization value that could eventually lead us to identify the unknown? So I'm going to be solving for HV here. I've inputted the two values in this case. I'm going to divide each side by 60 and get that my heat of vaporization is 709 joules per gram. Okay, so here's some of your own practice. See if you can identify which formula to use and also how to input the information correctly. So for number 1, we have how much energy is needed to boil 75 grams of water at 100 degrees Celsius. Now, boil is the key word that identifies that we're using Q equals mHV. The 100 degrees Celsius is extra information. You can see that we don't have temperature anywhere in here, but I do have mass, and because I know that I have water, I have my heat of vaporization. So I can input the 75, input the 2,260 joules per gram, and get my answer in joules. And really, I should be rounding that to reflect the 3 sig figs present. All right, so that is it. We're going to practice this a bunch tomorrow, kind of combine it with what we did yesterday with the Q equals MC delta T, and that wraps up Unit 2.